When I was a child, I remember the first time I encountered the word vector was in the context of graphic design. I've always loved drawing, so when my father told me that there was a short graphic design course being offered near my neighborhood, I said, why not? So I enrolled the course, and in the very first lecture, the teacher explained the difference between vector and bitmap images. If you don't know what those terms mean, here's a quick explanation. When representing an image digitally, we essentially have two ways of doing this, using vectors or using bitmaps. A bitmap image is a rectangular grid of squares, each one of a particular color. By putting many of these squares together, called pixels, we build an image. On the other hand, a vector image is not made up of pixels, but of mathematical formulas. Wait, what? Yes, mathematical formulas. You heard well. And if you don't believe me, just Google vector versus bitmap. And you'll see that every article essentially says what I've just told you. Maybe just replacing the word formula with equation, function, or algorithm. So if you've never done graphic design before, that might sound a bit intimidating. Those vector graphics must be hard to make, you may think. But nothing could be further from the truth. There are many vector graphics programs out there, like CorelDRAW or Illustrator, and they are actually pretty intuitive to use. So, why am I telling you this story? Because although I really enjoy the colors, the explanation of what vector graphics are didn't quite satisfy me. With a bitmap, you can literally see how pixels form the image. But in a vector image, where are the functions? And how do they compose the image? That's exactly what I decided to explore today. So let's begin. In school, we learn about functions and how to draw them on paper. You've probably seen polynomials, exponentials, and even trig functions. So maybe the answer is in that direction, right? Well, let's try. If we want to draw straight lines like these ones that I'm drawing right now, we can use the line equation. So problem solved, right? Not quite. Because as you noticed in the program, you should be able to control the line by its start and end points. So we need a way to transform the information from those points into our b and m. So let x0, y0 and x1, y1 be the coordinates of our points. How do we translate them into m and b? The m part is easy because, as you may remember, it is precisely the slope of the line. What about b? Well, since both p0 and p1 belong to our line, the coordinates must satisfy the equation. So we can plug either p0 or p1 into the equation and solve for b. In either case, we'll get the same result. Let's do it for p0. And there it is. Now we have b and m. And our final equation is... But wait! If I had used p1 instead, wouldn't I get a different equation? Good question. And it seems reasonable to think that we would, since we are solving it differently. However, as I mentioned earlier, you get the same value for b in either way. Surprising, right? But don't just take my word for it. Do the computation yourself. I encourage you to try it. Okay, now how can we verify that our equation is correct? In the past, this was done manually, but today we have computers and tools like Desmos. In Desmos, I can define a movable point by writing any point and giving it a name, like P0 or P1. Once defined immovable points, you can, well, move them wherever you want. And now, to retrieve their coordinates, I can append .y or .x at the end of each point name. So now we know this, we can translate our previous line equation into Desmos. And look, we now have a fully adjustable straight line. Great! However, there is a small issue. Our line is infinite, and we want a line segment, like in Inkscape. But that's easy, we just restrict the x range from x0 to x1. But now we have other problem. If you play with the line a bit, you'll notice a bug. And this is when P1 is behind P0, the line disappears. Fortunately, there is an easy fix for this: parameterization. But we'll skip that part in this video for simplicity. For now, let's celebrate and move on to something more interesting: curves. To draw a curvy shape, we have many options: polynomials, rationals, exponentials, trig functions, and so on. But when you get familiar with them, you realize that polynomials are the most flexible and easiest to control. In fact, we've already used one. After all, the line equation is just a first-degree polynomial. So the next natural step is to use a second-degree polynomial, aka a quadratic function. But don't run away, because we are not going to need the infamous quadratic formula in case you were worried. Okay, so what can we draw with this function? Parabolas. Any kind of parabola. Thicker, thinner, whatever we need. Now, as with the straight line, we need to find the numbers a, b, and c based on our control points. How many points? Well, if 2 points were enough for the line, then 3 points should work here. So here's the problem. Given 3 points, P0, P1, and P2, in the plane, what is the equation of the parabola that passes through all of them? Let's solve it. This time, sadly, we don't have any direct interpretation for the constants a, b, or c, so we can't do the same trick as we did before to find m directly. But that's not a problem, because we can always use a general principle that we've already stated earlier. All the points that belong to a curve must satisfy its equation. And the great thing about this is that it not only applies to functions, but actually to any kind of curve defined by an equation. That is essentially what it means for a curve to be defined by an equation. So, if our curve passes through P0, then the coordinates of P0 must satisfy the equation. And we can say the same for P1 and P2. I know that may look a bit intimidating, but remember, we are solving for a, b, and c, and the values of x are known. So it's actually just a linear system with 3 unknowns. There are many methods to solve this: elimination, substitution, and so on. But while those methods work, they do not give us a compact formula, which would be more useful if we later want to implement this in a computer program. So what can we do? Fortunately, linear algebra comes to the rescue. We can first write this system in matrix form, or symbolically, x times a vector equal y vector. If you've studied matrices before, you're about to see their real power. But if you haven't, you can just think of this as a neat shorthand to handle multiple equations at once. So why is this useful? Because now we can apply Cramer's rule to solve for a, b, and c using determinants. Here, d is the determinant of the system, And d sub a, d sub b, and d sub c are the determinants of the matrices obtained by replacing one column at a time with the wise column. If this sounds a bit abstract, don't worry, I'll leave a link to another video or article that explains matrices and determinants in more detail. But here's a quick intuition. Imagine a simple system with two equations. To solve this system, we usually do the standard elimination. But here's a trick. Instead of writing the full equations every time, we can save time and ink by only keeping track of the coefficients. That's what we call an augmented matrix. So instead of manipulating the system, we're just going to manipulate the terms of this matrix. If this is the first time you're seeing this, don't worry. I'll show the row operations side by side so you can easily follow it. You can pause if needed. So here is the solution of our system. Notice something? Yes, both denominators are the same. And moreover, they can be calculated as a simple combination of the coefficients of the system matrix. This cross multiplication is very useful in linear algebra, so we give it a name, the determinant. Why? Because it helps us to determine the solutions of a system. And while this example was just for a 2 by 2 matrix, it actually generalizes to any n by n matrix. So now you know this, here's a challenge for you. What are the matrices whose determinants are the numerators of these solutions? Again, if you haven't seen this before, I really encourage you to pause for a moment and try to do it. Okay, I hope you took a moment to think about it. Here are the answers. Do you see the pattern? Exactly. The first unknown. Do you see the pattern? Exactly. For the first unknown, we replace the first column of the system matrix with a column of constant terms. And for the second unknown, we do the same with the second column. And the same procedure generalizes for a 3 by 3 system, or any system or any size. So, returning to our problem, I hope you now have a better understanding of what these equations mean, and a rough idea of where they come from. Okay, enough theory for now. It's time to test it. I'm in Desmos again, and I'm going to create a third point. And now let's choose these points for our curve. And now I'm going to use Wolfram to compute the coefficients by using determinants. We repeat the procedure and we get the 3 coefficient. So this is now our final formula. And look, the parabola passes exactly through the points we defined. We did it! Now let's go one step further. 4 points. We'll go quicker this time, since the previous cases were good training. And remember, we're not going to grind through this forever. The goal is to study the simple cases to spot patterns. So now we have 4 points. And this time we'll use a cubic and not a quadratic because we need an extra parameter. As before, each point lies on the curve, so we get 4 equations, which in matrix form look like. And again, the coefficients can be found with Cramer's rule. So by this point you might suspect that if we repeat the process for more points, we'll get the same equations but with more and more unknowns. And you're right, So we are done, right? Well, yes, if it were not for a little problem that I've been hiding so far. And it has to do with how we actually compute the determinants. Previously, I showed you how to compute a 2 by 2 determinant, and it was easy. For the 3 by 3 case, you need more operations, but it is still pretty manageable. However, as you increase the size of your matrix, the operations needed to compute the determinant grow wildly. Specifically, they grow as n factorial, which is one of the worst things you may encounter in terms of complexity. It's really a nightmare, even for computers. And if you don't trust me, just write 10 factorial in Wolfram and you'll see that although 10 is relatively a small number, the result of this operation is bigger than 3 millions. So, although our main focus is not efficiency, we definitely have to do something about it. And the hint that will guide us is the shape of the matrix of our systems. So here I'll show them again. Do you see any pattern? Yes, exactly. Each row is built from powers of the x coordinates. These kind of matrices are called Vandermonde matrices. And the nice thing about them is that their determinant has a very clean formula. Let's see why. For the smaller matrix, the determinant is simply x1 minus x0. Now, for the 3 by 3 case, we follow a similar procedure to what we find Cramer's rule in the 2 by 2 case. That is, we're going to add and subtract to generate zeros in our matrix. So I show this quickly because it's just computation, and you can always pause to verify if you want. Great! Now we have an upper triangular matrix. I hope the reasons for the name are obvious. And what is interesting about this matrix is that you can always find its determinant by simply multiplying the diagonal elements. So the determinant is x1 minus x0 times x2 minus x0 times x2 minus x1. And for the 4 by 4 case, you can repeat the same idea, and I encourage you to try it. And the result you'll get is the following. Okay, now we have enough examples to extrapolate. Do you see the pattern? Say, if I ask you for D5, what do you expect to get without doing any calculation? Here's the rule. In general, the determinant is the product of all pairwise differences xy minus xj. In general, the determinant is the product of all pairwise differences x of I minus x of j, with I greater than j. Let's see how this works. For n equal 2, we have this inequality, so the only possibility is for I equal to 1 and j equal to 0. For n equal 3, we have this other inequality. So now I can be 1 or 2 and j can be 0 or 1. But remember, j must be less than I. So the combination 1, 1 is not allowed. Thus, we have this result. And the process just repeats for n equal 4. So you should easily get this. And finally, for n equal 5, this is the answer. By the way, you can also write this more compactly by using a big pi, aka the product symbol. But don't let it scare you. It's just notation. So there it is. That's the Vandermonde determinant. And the reason why it is so useful is that it reduces the number of operations dramatically. Great job! We're essentially done. Now, let's take a step back and remember what we've discovered. First, we started with the simplest case, a line, and succeeded. Then we moved up to the quadratic and saw how matrix algebra, especially Cramer's rule, helps to solve for the coefficients. Finally, we realized that our matrix wasn't just any matrix, it was a Vandermonde matrix, which gave us a neat shortcut for computing its determinant. A big win when we think about it coding it later. So far so good, now let's test this idea. For now, I'll skip the coding part and just use Wolfram to find the coefficients. So let's test first for 4 points. So we choose the points, we compute the coefficients, and we throw that into Desmos. And perfect! The curve goes right through all the points. Now we add one more point and repeat the process. And look, it's great again! At this point, it seems like our method works perfectly, but unfortunately, it doesn't, and I'm going to show you why. But before doing that, I encourage you to pause and experiment for yourself. Pick your own numbers, compute the polynomial, and see if the curve really does what you expect. Do you see anything wrong? Well, here's an example where everything breaks. I was trying to draw a Nike-like shape, so I came up with these points. But look at the graph. It's wrong. Completely wrong. It oscillates enormously and it doesn't represent my original idea at all. Why does this happen? Well, the explanation lies in the nature of polynomials. And to better illustrate this, I want to show you that we already saw hints of this problem earlier. Remember our second example? The one that worked well? Well, look closely at the tail of the curve. What I wanted to draw was something like this. But instead, I got this. The tail didn't flatten out as I wanted. And that's a big deal because we're trying to build a tool that lets us draw any curve we want. So how to fix that? Perhaps we might think about adding more points, because more points equal more control, right? So I added one more point and computed a polynomial again. And here's the result. Still not flat. And if you keep adding more points, the curve will actually never truly figure out the plateau you want. It might look flat for a bit, but then it will deviate. Why does this happen? Let's break it down. An nth degree polynomial looks like this. So, if we want a curve to flatten out to the right, mathematically, that means that as x increases, we want our function to look like a constant function. And this can be written in the language of limits as follows. The limit of p of x as x tends to infinity equals to c, where c is of course a constant. That is what flatten out means mathematically. But here's the issue. As x gets large, which term of the polynomial dominates? Or, in other words, which term is going to be the largest as x becomes increasingly larger? Exactly, the one with the highest power. So the limit of p of x as x approaches infinity is just the same as the limit of this term. And there is the problem. No matter what a sub n you choose, this term is always going to increase without limit. Unless, of course, you let a sub n equal 0. But if a sub n equals 0, your polynomial is not going to be of degree n anymore. So it won't pass through all the points that you defined. And even if you do this, hoping for your curve to behave well enough for your purposes, the next highest power takes over. The same reasoning continues until all that's left is a constant term, which is useless for drawing curves. So here's the answer. Why do polynomials can flatten out? Because they always grow uncontrollably at the ends. But why do they sometimes work? And when do they work? The answer lies in the basic structure. Many polynomials can be written in the following form, where the r's are the roots. And as you can easily see, when we evaluate the polynomial at one of these numbers, we get 0, which means that the points r1, r2, and so on belong to our curve. And you can easily see these more clearly with the following example. And now, let me show you a few more examples and see if you can notice anything interesting. Did you see it? Precisely, all of them look wavy. And this happens because for the curve to pass through a root, it has to change its previous direction. And if you add more roots, you get more and more oscillations. So polynomials naturally fit curves that look like parabolic arcs, hills, or valleys. But they do not work for plateaus or sharp Nike swoosh shapes. And if you try to force a polynomial to do that, it struggles, because its nature is to oscillate, not to stay flat. That's why the tail bumps you saw weren't random. They were part of the identity of the polynomial. That's why the tail bumps you saw weren't random. They were part of its identity. One way I like to think about it is that when we model the polynomial with our control points, it's like we are essentially building something like the factorized polynomial. But now, our roots do not lie in the x-axis, but rather in a modified axis. The curve tries to oscillate, but we force it not to do so. And that is exactly what happened in our Nike example. The curve wanted to oscillate, and we couldn't control it. And there you have it. Now you know for which kinds of curves our polynomials are very suitable, and for which they are not. To finish, let's recap and reflect on all we've done. We started with a very basic question. How does vector drawing work? That curiosity led us to the project of building a simple graphics tool ourselves. To make that possible, we choose polynomials because they are simple yet flexible enough to define smooth curves. We set up the equations for the polynomial coefficients and quickly realized we needed to solve a linear system. To handle that systematically, we used Cramer's rule, which brought determinants into the picture. Then, we noticed something interesting. The determinant of our system had a special structure, a Vandermonde determinant, and we derived its formula. Finally, we tested our model and saw that it didn't behave well for all kinds of curves, which led us to analyze the types of curves that polynomials can represent and their limitations. Wow, that's quite a journey for a single question, isn't it? And here's the interesting part. While chasing this goal of creating our toy software, a lot of math appeared naturally. Linear systems, matrices, determinants, patterns in our special matrices, and even some ideas about polynomials and limits. Things you might have seen in school, but here they weren't random. They came as answers to problems we needed to solve. And that's the point. Math often feels disconnected because we rarely see why those ideas exist. One doesn't just wake up one day and say something like, I write numbers in a square and define a weird rule of multiplication. No, not unless you're Ramanujan. Rather, these things come from real questions, like the one we started with. And that's why I encourage you to keep asking questions. Ask how things work. Ask why someone invented a concept and what problem it solved. And don't stop there. Google it, explore, experiment, and trust me, even if you don't find the answer to your original questions, you'll discover a lot of marvelous things along the way. Thanks for watching.